Well, let's get started then on your first day of Calculus 2. And like I said, we're going to start with section 6.1. And we're going to talk about the natural log function. You know, I know you guys have seen the natural log function before, but it's probably a good idea to go over some of the properties, because you might have forgot them. We haven't really worked with them a lot since maybe your pre-calculus class, maybe your Math C class when you get it for the first time. So we're going to start with some of the properties, what you can and what you can't do with natural logarithm and with log functions in general, and how that's going to help us with our derivatives and some of our integrals. So let's talk about the properties. The first one. First one was kind of a nice one. Anytime you see this, you loved it because it meant if you had ln of 1 that was always equal to, say it again?
0.
Yeah, it's exactly right. So what this is, if you don't remember how logarithms work, logarithms say a base, what's the base here?
E.
E is the base. For any logarithm, you don't need to write this, but check this out. If we had this, for instance, this would be our base, that would be our power. Base to the power gives you the argument of the logarithm. So this would have an exponential notation like that. If you forgot all about logarithms, that's like a really crash course in logarithms, okay? So in other words, when we have a natural logarithm, that's based on, or the base is e, the natural number e. E is about 2.71, so on, so on, so on. So when we have this, this says, hey, e to the 0 power gives you, well, how much is anything to the 0 power?
1.
That's why this works. So anytime you see ln of 1, we automatically know that's 0. Show of hands if you feel okay with that so far. Good, okay, fantastic. Number 2. Anytime you have, and this is called the product property of logarithms in case you're wondering, anytime you have a product within any logarithm, including the natural logarithm, you can always break up that logarithm into two different logarithms. Do you remember how to do it? If I have log or ln of x times y, how do I split that up?
Plus y, ln.
Fantastic.
Plus y.
Product plus product. PP. That's funny. But anyway, so product gives you a plus here. So if we have ln of x times y, that's ln of x plus ln of y. One thing to remember here, these are not just one-way streets. So we can either expand by a product or we can combine two logarithms by addition. The only thing that you need to check on is that they have the same base. Now naturally, our natural log are always going to have the same base, so we're good to go as far as that goes. You guys okay with number 2?
Yeah.
Okay. Number 3. This one's really, really similar, and I'm imagining that even if you didn't know the property, which you probably do, you could probably figure it out. If we expand multiplication by addition, how are we going to expand division?
Subtraction.
Yeah, fantastic. Which one's going to go first, the ln x or the ln y?
X.
That's right. So ln x minus ln y. Again, we can combine them. We can combine two logarithms that are being subtracted, or we can expand a logarithm that has division inside of it. We still okay so far?
Yep.
Okay. And last one, this is my favorite one. I love this one. This one's called the power property. It says that anytime you have a logarithm with an exponent in the argument of that logarithm, we can do something with that exponent. What can we do with it?
Put it in front of our leg.
Yeah, that's great. So ln of x to the r, same thing as r times ln x. Now, how we use these is to expand or combine logarithms. It depends on what situation we have, but sometimes we'll be expanding, sometimes we'll be combining, depending on whether we're taking derivatives or integrals or doing something with that. So let's practice just a couple times. No calculus yet. I want to make sure that you guys can expand some of these logarithms. So let's start with that one. ln of 3x, and you know what, I want to make sure you guys know this, the ln goes in front of it. Ln is, it's not like multiplied by this argument, it's ln of that argument. It's a function of whatever your argument is here. So ln of 3x to the 4th all over 2y squared. Let's expand this as much as possible, just to get the feel for how this stuff works. So Give me one idea that you might have.
The minus.
Yeah, very good. We're noticing that right now we're kind of working from, and you did this when you did derivatives a long time ago, we're working from the outside in. We don't really want to start with moving the exponents forward yet because, well, we got a couple of them, right? Where would we put it? It doesn't really make a lot of sense. So expand from the outside in the big part to the little parts. The biggest part we see, the thing that combines all of this argument is division right now. So let's take care of that division. And what's division changing to again?
Subtraction.
Fantastic. Okay, so we're going to have ln 3x to the fourth minus ln. That's exactly right. True or false? Right now, it would be a great idea to move the exponents to the front.
No.
True or false?
False.
Why?
Because the exponent goes to x and y.
That's a great point. So do you guys see what he was saying there? He said because this exponent doesn't go to this whole thing, it's just attributed to that x, I can't move it forward yet. Now, if it had been like this, would I move it forward?
Yes.
That'd be fine. But if it's not, you gotta be real careful on that. Do you guys see the simple mistake that can really cause a problem, right? So watch the small stuff here. All right, well, if we can't move that forward, what's something that we can do with that logarithm? What do you think? How would I break them up?
ln of 3 plus ln of x to the fourth.
Yeah, you're exactly right. Because that's a product in there, I can certainly do that. Let's do the same thing over here. Okay, I want you to think carefully on what I've just wrote on the board. Am I right or am I wrong?
Wrong.
Some over here, why am I wrong? What did I do here?
The negative needs to go into both columns.
Fantastic. So if we're subtracting this ln, remember, if you expand this ln, this still means this, right? It still needs to be subtracted. So either you're going to draw those brackets or you're going to distribute that negative, that minus sign. You guys with me on that one? Again, be careful of small stuff. So we're going to do a couple steps right now. There's one thing I want you to do to expand this one more time. What can we do now with our logarithms? Say it louder.
Now you can do like the exponent to the front.
Yeah, that's absolutely right. And then I'm going to distribute that minus. So we'll have ln 3 plus 4 ln x minus ln 2. Nothing we can do there, but here we'll have minus 2 ln y. This, when we get to this point, there's literally nothing else we can do to expand this, make it any longer than what we have right now. By show of hands, do you feel okay with expanding our logarithms? Good with it? Any questions at all? What you're going to find out is that because we can do all this, what's going to be easier to take a derivative of? This argument or that argument? That one. That's way easier. That's a constant, for goodness sake. Derivative constants are, hey, that's fantastic. This going to be a piece of cake. This, 0. This going to be a piece of cake. So we're getting there, but by expanding logarithms, we make our derivatives and our integrals a whole lot easier when we're dealing with ln. Okie dokie? Okay. Tell you what, we'll try one more together, and I want to see what you can do on one of them. Just keep something in mind too. These properties, they're the only properties that we have for logarithm as far as expanding and combining. One big thing people do in math is they like to make up their own math, their own properties. Look, if they weren't listed on the board, you can't do them. So be real careful about what you can expand and what you can combine. So don't make up your own stuff. Just follow the things that I've given you. So let's see what we can do with this. Again, we'll do one more together and one on your own. So ln x squared plus 1 all over the square root of x. Tell me someone on the left-hand side of the room, you guys over here, if I want to expand this all the way, where might I start?
Division. I would say change the x to the 1/2, like the square root to the 1/2 first.
I can do that, sure. I can do that now or I can do it later. Do you guys see what he was talking about? The square root, we know that's 1/2 power, so we're going to do that ultimately either now or later, it doesn't really matter when. As far as expanding goes, where would I want to start? Would I want to start moving exponents forward? Would I want to start separating products or separating quotients? Which one?
You do the subtraction thing.
Okay, cool. So we know that this is the same thing as, well, since that's a quotient, I know I'm going to have subtract square root of x. One more thing, just a little side note for you guys. Whenever you're expanding, sometimes you'll have to put some parentheses in the argument of your logarithm, especially like right here. This is really ambiguous. It doesn't really say whether it have ln of x squared plus 1 or ln of x squared plus 1. You want to make sure you show that. Don't leave the little stuff hanging out, especially in calculus 2, because you get a lot. The way that you write problems is important. It's not meaningless like when you're doing Math 80, you almost never get it wrong, right? You just write anything you want. But here at this level, you really need to be careful about how you're writing things. So make sure you're accurate. Now, I like the 1/2. We're going to change in just a moment. What I want to know right here, can I split that up anymore? Can I expand that any longer? No, that's great. No, we can't do it at all. We know that if it was a product, we can expand it. But if it's plus, there's nothing that says we can expand plus. So if we can't expand the plus, we can't move the 2 forward. We're basically done here. The only thing we can do, and this was already said, that is actually a power, and that can move forward. That's about as good as we can get. We can't split that up for sure. We've already moved our power forward, and that's expanded. I want you to try one of your own. I'm going to give you a hard one. If you can do this one, you know what you're doing. Booyah. I think this deserves a booyah. Let's go for it. Show me what you got. Remember that what we're doing, we're from the outside in. Go for the big parts first and split off everything that you can. Follow only the properties that I've given you. We can separate products. We can separate quotients. We can move powers to the front. So do the best you can. By the way, when I have you do something like this, I'll typically walk around the room. If you have questions, by all means, please ask me. That's what this is for. When we have a cube root, what's the power of that cube root? Cool. So a square root, because we had a square root, we have 1 over 2. We got power over root, basically, the power of the inside over the root. So when we have a cube root, don't be putting crazy things like 2/3 or anything weird. It's just 1/3. Unless you have a power like this, if we had a cube root of x squared, that's when you would get a 2/3 power or something, okay? It's power over root. So we have, hey, no problem. The first thing I saw, I've got division here. This is containing this whole argument. So I'm going to separate that division by subtraction with a logarithm. I'm also going to change that power to 1/3 power, and that says I can move that out front. Next thing we're looking for is any remaining products or quotients in here. Do you see any other products in here? How many? 1 or 2?
1.
Good. You know, some people who just don't like trigonometry, they'll say, oh yeah, you got one right here. Is this a product?
No.
No, this is actually the argument of a sine. So this is really the angle of that sine function. So we are going to separate this product, but we can't separate this. It's not a product. So we'll do ln of x to the fifth. We'll do a plus sign because we got product plus ln of sine squared pi x. And we'll do minus ln of x to the fourth plus 2 to the 1/3. And lastly, anywhere you have an exponent of an argument, are we okay? Anytime we have an exponent of an argument, we're going to move it up front. So we have 5 ln x. The 2, can I move the 2 forward? What do you think? What does this mean when I have what does that mean?
X is to the fourth power.
Is it the x?
Fine.
Is it the function?
Function.
That's literally what that means. So whenever you see a sign squared like this, this is not being squared. If it was, I would have it here. Don't change your work, please, but watch. If this was being squared, I'd have it here, and I'd have that as the argument. That's how that would look. If I don't want to say that, if I want to say the function's being squared, I know it's a little weird, but people have gotten the habit of just writing it right there. That's the power of the entire thing, okay? The entire function of sine is being squared right now. So we have this, that's really a power, that's an exponent. We can move that to the front. Of course, our 1/3. Okay, we've broken it down. Can we go any further? Do you see any products, any quotients, or any powers that we can move? Let's check. No. This, well, that's connected. We can't separate addition. We can't move that power forward. We're completely done. Show of hands if you got that on your own. That's really good. You guys know what you're doing then. You know, just like we can expand our logarithms, we can also combine them. I just want to practice real quick doing 1 or 2 of those. Then we'll start talking about how we take derivatives of these things. You guys seem like really smart people, so we'll cut right to the chase. We'll do a hard one. So what I want to do here, I want to combine these logarithms to see if we can get as few logarithms as possible. In our case, we're trying to get 1. So 1 logarithm. So let's take a look at it. You know what you might have noticed is that we typically deal with our exponents last when we are expanding. So here, we're going to probably have to deal with some of these guys first, otherwise we can't combine them. Does that make sense? In order to combine our logarithms, when you notice those properties earlier, it was log x plus log y gives you log of xy, or ln x plus ln y. There was no numbers up front, in other words. We have to move our numbers up front, our coefficients to exponents first. So tell me one thing you're going to do here. Should I deal with the 2/3 first?
No.
That one we can't, okay? That's out there. This is going to be the last thing we do. Should I deal with the 5 first? Yeah, that's got to move up. And the 1/2 has to move up, and the 4 has to move up. So we'll leave that 2/3. It says order operations anyway, really, doesn't it? It says 2/3 is outside. Deal with this stuff first. Put this all together, then do the 2/3. So inside of our bracket here, we got an ln of x to the 5th. We've got an ln x squared plus 1 to the 1/2. We got a minus ln of x minus 2 all to the 4th power. And I'll finish the frame. Okay, let's keep on working. Right side people, you guys. What's the next thing you might want to do? Say what? Sure. You can actually do both at the same time if you really know what you're doing. If you know this is going to be combined by multiplication, and this one's going to be combined by division, we're just going to have this times this all over that. Just do me one favor. If you're going to combine these things, please don't write different logarithms. It becomes one logarithm. It never becomes ln over ln. That's not the idea. We're getting ln of this argument times this argument divided by that argument, all in one little piece. So the 2/3 is still hanging on. We got ln, well, we got x to the 5th. We know plus is going to give us a product. Tell me one other thing you could do with that 1/2 power. What could you change it to if you wanted to? All over, you were like my little math robots there. It was awesome. Square root. There we go. Okay, as if it's not ugly enough, we can do one more thing. What can we do now? Now that we look at that, that's a coefficient, right? In fact, I don't even really need these brackets if I didn't want them. The 2/3 could go right there. If that's a coefficient of a logarithm, I can move that up and it becomes a power now. So this, our very last step, is ln x to the 5th, whole bunch of nasty crap. And then the whole thing, now with the bracket inside, you do need the bracket inside to the 2/3 power. Okay, that's about as in-depth as I want to get. Do you guys feel comfortable on expanding and combining logarithms? Probably some good practice, right? Because you haven't seen it in a while.
Could we have, in that first step, it would have been okay to just distribute the 2/3, you just would have ended up with smaller exponents at the end?
Absolutely. You could do here and here and here, and then move those up. Here and here and here, and move those powers up. You'll notice that you get the same exact thing because, well, what's interesting is that when you distribute, you multiply, don't you? You multiply and you multiply and you multiply. What do you do when you take a power to a power? How about that? It's the same stuff. So even if you took a power to a power, you're still multiplying. You get 10/3. Same thing would happen here. You get 10/3. Okay, so either way you go, you'd be fine. I like this way because this is all to one power. That's just preferential though. Good question. Thank you for that one. Any other questions at all? Are you ready to move on to finally get to some calculus?
Good.
Okay, now that we've covered that, we will use it. Trust me, we'll use it a lot. I want to refresh your memory on one more thing, and then we're going to start talking about some integrals and get on to what in the world we're going to be doing with all this junk. So, the last thing we got to cover. Do you remember the graph of this function? Okay, do you remember the graph of this function? I see a lot of already. Let's talk about it. When you take a positive number, which this is, E is approximately 2.7, you take a positive number to any power, what are you going to get out? You're going to get out a positive number, that's right. Can you ever get out 0? Can you ever get out 0? No. So what automatically know that this function is not going to cross the x-axis. It's always going to be above the x-axis. Does that make sense to you? Okay, so how about this? What if you were to plug in 0 here? How much would you get?
1.
So we know it's going to cross the y-axis at precisely 0, 1. You said that it's always going to be above the x-axis because it's a positive number being raised to a power. It has to be above here. You're never going to cross this line. Does that make sense? Now, when I plug in big numbers, does this thing get really big or really small?
Small.
Big numbers. Take 2 to the 4th, 2 to the 8th, 2 to, this is about 2. Is it going to get bigger or smaller?
Bigger.
Bigger, way faster. What's going to happen over here? Because when you have e to the -2, which is what these are, that's the same thing as 1 over e squared. Does that make sense? When you have a negative exponent, you put it on the denominator. So as that power gets smaller and smaller, more and more negative, that denominator gets bigger and bigger and bigger and bigger. 1 over a really big number tends to be close to 0. Is it ever going to touch 0? No. But it's going to look like this. That's the graph of e to the x. Tell me something, somebody out there. What's the relationship between this function and that function?
Inverse?
Very good, they're inverses. What inverses are, graphically, are a reflection across the y equals x line. So if we want to find out that graph, it's really stemming from this graph. In other words, if I take this diagonal right here, and I just flip it right over, that's going to give me ln x. So tell me, if 0, 1 is on my e to the x function, if 0, 1 is on my e to the x function, what has to be on my ln x function? Good, because inverses just flip the x and y. Did you know that about inverses? That inverses really just flip the x and the y? It's a reflection across y equals x. So it's just flipping those coordinates, really. So if we have 0, 1, an inverse would have 1, 0. If this is asymptotic to negative x, this is asymptotic to negative y. Which means our graph looks about like that. That's the graph of ln x. You kind of need to know the graph of what we're working with because the properties are going to make a whole lot more sense to you. For instance, the very first property said, hey, when you plug in 1, you're going to get 0. Hello, when you plug in 1, you get 0. Remember that ln of 1 is always 0? It's on the graph, it's right there. Can you plug in 0 to ln? Do you have a calculator? Have you ever tried to plug in 0 to ln? Press ln 0 if you have a calculator right now. Try it. Have you tried it? Do you have an error?
I got it.
Did you get? If you tried it, if you press ln 0, hopefully, if your calculator's not broken, it's going to give you error. What are you trying to kill me? That's what it's saying. You're breaking its heart, really, is what you're doing. Because you're supposed to know this about ln. Can you plug in 0? It's undefined. It's undefined. Can you plug in a negative to ln, do you think? It's undefined. There's nothing there. So when you realize what the graph looks like, you kind of understand. You understand a little bit better about why you can't plug in, why you can't have ln of negative 3. It doesn't make any sense. You can't have ln of 0. It doesn't make any sense. ln of 1 gives you 0. It's on the graph. So when you get a better picture of what the graph looks like, ln makes a little bit more sense. Show of hands if you feel okay with the graphs of these things. Did I do it well enough for you? Understand where it came from? Fantastic. Now, let's see how good you are, how much you remember about one of our favorite things in the world. You ready? Right off the bat, man. I'm going for it. Holy cow. Oh dear, you didn't think it was going to be this fast, did you? Don't worry, you should know this stuff, right? You should know the integrals. Integral, oh my gosh, integral is the same thing as what we call an antiderivative. Basically, not basically, it is the inverse of a derivative. Just going backwards. Do you remember how to take the integral of something like that, where we have x to the third dx, which says inverse with respect to x, changing x?
Add something to the exponent.
Add something,
Add
add
1.
1. Very good. So the power rule backwards said, well, hey, if you take a derivative and you subtract 1, you move forward and you subtract 1. Here we're going to add 1 and then divide. So if we did x to the 5th as a derivative, and that said move this forward, then subtract 1, we're going to do completely the opposite thing now. We're going to add 1 and divide by that new exponent. So this said multiply by the old exponent, then subtract 1. This one says add 1 to the exponent, then divide by that new exponent. That's exactly how you take an integral. And I'm missing one thing. What am I missing?
Plus C.
Why do we have a plus C?
Constant.
Because it's an indefinite.
what we're doing here is we're finding a family of curves that work. You see, that plus c, when you take a derivative of any constant, is going to go to 0. So we have a whole family of curves that work. The only time you don't have a family of curves with an integral is if you have either a definite integral or you have an initial condition, which we'll talk about later. Y'all okay with that one? Basic, basic? Okay, let's move on just a little bit. What would happen if I had a constant inside of my integral?
Move it up.
Always move out a constant provided it's being multiplied, not added, not subtracted, but multiplied by whatever my function is. So sure, we can move that outside. We can go 4 times the integral. Just like derivatives, we could do this. X to the 5th dx. Tell me, left side people only, just you guys, tell me the integral of x to the 5th, please.
X to the 6 divided by 6. 1 6 times x to the 6.
Cool, okay. However you want to write that's fine. So we'd have 4, just don't forget the 4, x to the 6th over 6 plus c. And what are we going to do with that?
Simplify.
Absolutely. However you want to write it, if you want to do the 2/3 x to the 6th plus c, or 2x to the 6 over 3, I don't care. Whatever you want to do there is fine. Still okay so far? Okay, stretch your brains just a little bit. Think back to this one. Oh dear. Now, I want you to really think about what happens with derivatives before you answer this. Unless it's just burned in your memory, you know it. But please think before you answer this question. Integral of sine x dx. Integral of sine x.
Negative cosine x.
Cosine or negative cosine? Which
Negative
one?
cosine.
Why isn't it positive cosine?
Because there was a negative sign.
Good. The derivative of cosine is negative sine. So if I'm trying to get a positive sine, well, the appropriate antiderivative here is negative cosine x. Watching too much Scrubs. Dr. Cox, never mind. Bless you, thank you. Yeah, plus c, exactly. Last one. Let's try that one on for size. What are you going to do with that problem?
The quotient.
Quotient rule works for derivatives, but like where your head's at. Substitution. Oh, I love substitution. I love substitution. If, oh my gosh, your teacher should have taught you this, and it wasn't me. If the derivative of what you're trying to substitute is actually in the integral. So find a piece up there, take a derivative. Do you see that piece in the integral? You do? I hope not. That gives you 4x to the 3rd, right? I don't care about the 4, but do you see the x to the 3rd? I don't either. Plus is on the denominator, so that would be a problem too. Think easier.
Separate x
Separate
squared to the top.
So what do you mean separated?
like x to the 4th over x squared minus negative 1 over x squared.
Let's do that. So this is kind of a nice trick. Anytime you have a single term denominator, you can always separate it. You always make different fractions out of that. So we could do x to the 4th over x squared minus 1 over x squared. Yeah, absolutely. That's fantastic. Tell me the next thing we're going to do. Someone over here on the left-hand side. What now?
Simplify it right
Let's simplify one thing for me. What do you get?
now. It'd be x squared on top minus 1 over x to the x squared, but you can make it x to the negative 2.
Yeah, perfect. Go ahead and do the integral for me on your own. Let's see if you can get that. Remember that while you can split this up into integral minus integral, you don't have to. You can just take it piece by piece. So take the integral of this piece minus the integral of this piece. Of course, you can get negatives, you can change the minus to a plus. You can do it just piece by piece when you have multiple terms in there. You don't have to separate it all. By the way, just a little bit of notation for you. When you do the integral and you get x to the third over 3, or 1/3 x to the third, you guys got that, right? I know this because I saw a lot of you in the math lab. Some of you, when you do integrals, by the way, what's this become? Good, you add 1 to it and you divide by whatever the new exponent is. Did you all get that far? Okay. Some of you like to do this. Some of you like to take integrals and go, oh yeah, I just took an integral. What that symbol means is that you're supposed to take the integral of whatever the argument is next. If you've already done the integral, this does not go here. Okay, you've already done that, so erase that. Do you understand about the notation here? This is telling you what you're supposed to do. This says take an integral, evaluate it from 1 to 2. This says take an integral. Haven't you already done that? If you want to show the evaluation, the appropriate way to show it is to put it over here from 1 to 2. That's where you put that. You go, okay, I've done the integral, it's a definite integral, now I'm going to evaluate from 1 to 2. Of course, you want to make it a little bit nicer looking before we do that. We'll do x to the third over 3 plus 1. Do you guys see where I'm getting the plus 1 over x from?
Yeah, the negative.
Good, cool. And then we would evaluate it. Go ahead and evaluate it. Remember that when you evaluate, we plug in this number first, we figure out what that answer is, and we subtract after we plug in that number. So plug in the 2, figure out what you get, subtract after you plug in 1. Did you get it? What'd you get?
11/6.
11/6, double check.
I agree.
11/6? 11/6? Cool.
11/6.
We're not going to spend a whole lot of time in here waiting for this. I know you guys can do this. I just want to make sure you see some finer points of doing integrals. That way you don't get stuck on some of these easier ones, okay? Don't make it harder than it is. That's a lot of what this class is about. Don't make it harder than it is. So if hands be okay with our integrals? Okay. I have one more for you. Give me ideas.
Move the x to the top.
Okay. That looks pretty painless. Let's try that. So every other time we had this, we did, let's see, where were we? Add 1, divide by the new exponent. Are you listening? Add 1, divide by the new exponent. Let's do that. Let's add 1 to this. What do you get? X to the, well, that's fine. We get 1 divided by, that's not fine. No, that's not fine at all. That gets pretty nasty. So what in the world are we going to do? Oh my goodness. Let's give up. Calculus 2 is over. Let's just go on. Well, this isn't going to work. This is not good. This is not good at all. Well, let's think a little bit more about this. First things first, do you know what the graph of 1 over x actually looks like? Think about it for a second. Do you remember what the graph of 1 over x actually looks like?
Approaches 0.
It does approach 0,
It's like,
and it approaches infinity. It's like this little, actually, got the wrong sound effect, my bad, sort of thing. What I'm going to do, and you'll see why in a minute, I'm going to graph 1 over t. You'll notice that 1 over t has a dummy variable in place of x. You'll see why in a second. This graph, if this is t and this is y, looks about like that. This graph looks like. As I get closer to 0, my number gets really, really big positively. As I get closer to infinity, my number gets really, really small, but it's still positive. You with me? Okay. True or false? That function's continuous, anything bigger than 0. Absolutely. There's no holes, there's no gaps. True or false? It's differentiable anywhere past 0. Are there any sharp points? No. So this is continuous and differentiable. Well, what that means by the fundamental theorem of calculus, I'll write this out for you. Because 1 over t is continuous, on the interval that we're trying to talk about here, I'm going to abbreviate, by the fundamental theorem of calculus part 1. Fataki, I made that up. By Fataki. By fundamental, it sounds kind of cool though. I think it'll catch on. My YouTube people will make sure it catches on. Fataki. By the fundamental theorem of calculus part 1, this thing, or sorry, we must be able to find some differentiable function that gives us this thing. Because this function's continuous on our domain we're looking at, by the fundamental theorem of calculus, we absolutely have to find some differentiable function. We're going to call it capital F of x, big F of x, such that this is true. Such that f of x, big F of x, equals the integral of our function from some defined point to x. That's got to be the case. If you don't believe me, look up the fundamental theorem of calculus part 1. That's exactly what it states. So this is just by definition. I'm not making anything up here, okay? This says that this integral has to exist. It's got to exist because it's continuous, and fundamental theorem of calculus part 1, which is proven, says it exists. It's got to be there. Also says, this is just the corollary, that if I take a derivative of it, that would be, again, since these things have to be equal, it would be a derivative of this thing. This you have seen before. This is what you were taught in Calculus 1 about the fundamental theorem of calculus. It says when you take a derivative of an integral and you go from a defined point to x, what this is just 1 over x. Do you remember that?
Yeah.
Which is the function in terms of x. These were the easy ones you had on the test where it's like, oh, I got a whole bunch of t's. I just put an x everywhere I see t. Do you remember that one? That's basically what it said. And now you know a little bit further. What this is talking about is that if your function is continuous on this interval, you have to be able to do this. You have to be able to take the integral of that function, and it's defined. It's a differentiable function. And when you take the integral of that function, it gives you back your original function. So basically it says there's got to be some function that gives me little f of x when I take a derivative of it, and the integral of little f of x actually exists. That's the basic idea here. Now what we do to make it just a little bit easier, we typically define a to be 1. It really doesn't matter as long as it's bigger than 0, and this thing works out pretty nicely. So here's a couple things I want to point out to you in the last 5 minutes. You know what, I'll write it for your team. It turns out that the following things are true. Sorry, my bad. That should be a T there. Change your notes. That needs to be a T. I'm sorry. You get the X when you evaluate from A to X. My bad. So first thing, it turns out that ln x is actually equal to the integral of 1 over t from 1 to x. That's a true statement. It's by definition. So that's a definition that we have. Also, check this out. This is where the fundamental theorem of calculus part 1 is going to come in. Watch very carefully, okay? Did you know that you can do anything you want to an equation as long as you do it to both sides?
Yeah.
Including take derivatives. Which is cool. Let's check this out. Do you believe me that this is true?
Sure.
You have to, darn you, because it's a definition. It's true. If I take a derivative, because I said so, if I take a derivative of both sides, check out what happens over here. If I take a derivative of ln x, I have to take a derivative of this nasty crap. That's a little crammed. Sorry, make that a little better for you. Derivative ln x equals derivative Do you see this piece anywhere else up on the board that we talked about? What's it equal? Okay, check it out. By fundamental theorem of calculus part 1, we know that this is true. By definition, we know that this is true. So by the transitive property, if this, we can take a derivative of both sides, this equals this part equals this. You know what, I'm going to do it. I'll write over here so you have more room. Did I lose you? Do you guys have any questions on that? I don't want to lose you on that one. It's kind of a cool little proof. I hope it makes sense. So here's what you need to know. This is a really long way to say, here's what it is. So here's what it is. Here's what you got to know. The first thing, yes, we can now take integrals of 1 over x. Check it out. If the derivative of ln x equals 1 over x, that means the integral of 1 over x equals ln x. The only thing that we have to be careful of is that we have to have an absolute value around the argument of ln. Naturally, we can't have an argument that's negative. Remember the picture? Remember the graph? We can't have negatives in there. So here's what we say. We say this equals the ln of the absolute value of x, of course, plus c. That's number one thing. So when you're taking an integral and you come across 1 over x and you go, holy crap, if I add 1 to the exponent, I get 0 over 0. If I get 1 over 0. We can't do that. Well, now you have something for that. We've proven it over here. When you take the integral of 1 over x dx, you get ln absolute value of x plus c. Are you guys okay with that one? Did you get the reason behind it? If the derivative of ln x equals 1 over x, almost the reverse is true. The integral of 1 over x gives you ln of absolute value of x. If you have a definite integral, the same thing is true. We get ln x from a to b. If you're wondering, well, wait a minute, Mr. Leonard, wait a second. I thought you said that you had to have absolute value here. Check out what would have to happen for this to be an integrable function. You'd have to have something that doesn't go across 0. Do you see what I'm talking about? You'd have to either have both positive, both negative. We're talking about both positive here. So if you have both positive, you're never going to have that negative argument inside the logarithm. Do you see what I'm talking about? So we're fine as far as that goes. The second part, if we take a derivative of ln absolute value of x, we are going to get 1 over x. This is right here. Derivative of ln x equals 1 over x. We have the absolute value, so it looks a little bit more like this. Really, you're not going to see a whole lot of the absolute value unless you can have a function which goes negative, like cosine or something. Okay, you're going to see that in a little bit. So really, this or this. It doesn't really matter. It's kind of all this is saying is that, hey, your argument's got to be positive, so you make it positive. Should fans feel okay with that one? Okay, tell you what, I know we haven't done a whole lot of examples. We are going to get to that next time. So today we're going to do a whole lot of examples with derivative of ln. Last time what we learned was the expansion and the combination of natural logs. We also learned a little bit of calculus behind it. We learned that if we take the derivative of ln x, it's 1 over x. We're going to do the integrals in just a bit, but I want you to practice some of these derivatives right now. Before we get to it though, there's one thing I want you to recall from your Calculus 1 class. It was this. It's if you take a derivative of some function with another function of x inside of it. We called that, do you remember what that was called?
Chain rule.
Yeah, that's right, it's a chain rule. So if you remember the chain rule, what the chain rule said to do was take the derivative of the outside function, in this case f, I call it the outside function, it's just like the big function, what's containing everything. Take the derivative of f, leave the inside alone, and then multiply by the derivative of the inside. Do you remember doing that? So in this case, it would look like this. It would be f prime of g of x. You'd leave that alone, and then you'd multiply by the derivative of g of x. Or you just say g prime of x if you want a kind of mixing notation here. One quick example, if you want a really quick, like little sub-example here. If you did like the derivative of x squared plus 1 to the third power, if I asked you for that derivative, what we would do here, I'm not going to ask you to help me out on this one because you should know it. I'm just going to go really quick through it. This would be a chain rule. Some people call it the general power rule. It says the big function is something, a function to the third power. That's the big function here. Do you see how it contains everything? It says you bring down the 3 like you normally would. You leave the inside alone. Whatever's here goes here. You subtract 1 from the power just like you normally would. Notice 3, subtract 1 becomes 2. But then you multiply by the derivative of whatever the inside function is. Our g of x in this case would be x squared plus 1. Do you guys recall that? Show of hands if you remember that. Okay, and then of course you do the derivative, you get 2x, you pull it out front, and you'd be done with our derivative. I'm not going to finish that off for you, but that's the idea. We can do the same thing with ln x. I want you to consider what's going on here. If we have a derivative of ln with some function inside of it, in our case right now, this f, the function f is just ln. So the function ln, it takes the place of the function f right here. Does that make sense to you? Ln, natural log is a function, so it's taking the place of f. If we have any sort of function of x inside of that, what we're going to do here, we're going to do the chain rule. The chain rule says, all right, well, the first thing you need to consider is take the derivative of ln. What's the derivative of ln? What's the derivative of ln x say to do? You put 1 over... So you put 1 over whatever the function is. In this case, this is really easy because we had a function of x. It was just, well, the derivative of x is 1. Really what you're doing here is the chain rule. It says you're putting 1 over whatever's here. So 1 over x. And if you think about it, it's kind of weird, but if you think about it, if you multiply by the derivative of the inside here, which is x, what's the derivative of x? So it's not, hopefully it's not 0 because the whole thing would go to 0. It is 1. So we don't show that because the derivative of x is just 1, but that's really what you're doing here, okay? You're doing 1 over the inside times the derivative of the inside. The same thing works here. We're going to do 1 over the inside times the derivative of the inside. What I want to be sure is that you guys see both ln at work and that you see both the chain rule at work. Do you guys see both those things at work right now? The 1 over g of x, that's the same thing we're doing here. This is 1 over x. It just so happens we're calling the function inside g of x. So 1 over the inside, 1 over the inside, times the derivative of the inside, times the derivative of the inside. That's the chain rule with respect to ln. Show of hands if you feel okay with that one. Okay, we're going to practice that in a minute. For those of you who had a different type of notation for chain rule, I can give it to you this way as well. It means exactly the same thing. It's just some people like to see the u here, where u is a function of x. So if you have ln of u where u is a function of x, it looks just a little bit different. I hope you understand it means the same thing. You put 1 over u, you can see it's the same exact thing, times the derivative of u with respect to x, du dx. Same idea, just a little bit of different notation. What do you say we practice some examples right now? Would you like that? Okay, let's go for it. I promise you, these really aren't that hard if you keep in mind this is a chain rule. What a lot of people will do here is they'll forget to do this part. Just like a lot of you in your Calculus 1 class, when you first learned it, well maybe not a lot of you, but some of you forgot to do this a lot. You probably did, especially with like sine of 5x. You know, where 5x is inside. I know when I taught Calculus 1, a lot of people forget that well, it's not cosine of 5x, it's 5 cosine 5x, because you have to take the derivative of the inside. Same thing happens here. Don't forget that when we're doing logarithms, you still have to take the derivative of this piece. It's kind of like two derivatives. Derivative of ln is here, derivative inside is here. Let's practice them. Okay, so we got a derivative, we got ln. You guys seeing what I'm talking about? A function within a function here? We got a function of x inside the function ln. So the first thing that our chain rule says to do is, all right, take the derivative of the outside function. In this case, the ln function contains everything. So if we take the derivative of ln, it says you're going to put 1 over, I don't even care what's here, you put 1 over whatever's on the inside. So we're going to have 1 over 3x squared minus 1. Looks a whole lot like this idea right now. You're taking a derivative of the power, but you're leaving the inside alone. Taking a derivative of ln, you're leaving the inside alone. Now what do we do? Leave it, keep going. Keep going by multiplying by what? Sure. I would like to see this work right now when you guys get all advanced and you're in 4C or whatever. Do whatever you want, okay? But right now I want to see you doing this. That way if you make a mistake, I can see where it's coming from. So I want to see your work on these problems. I want to see the 1 over this. I want to see times a derivative, some form. You can use prime if you want. I prefer the ddx because when I teach calculus, I tell people, hey, follow the ddx. Wherever you have a ddx, that's where you're doing derivatives. That's where you're doing calculus, all right? So if you show that, it's going to let you know what you do next. So in our case, we have derivative of ln, no problem. 1 over the inside times the derivative of the inside. This lets you know where you're doing the calculus next. This, you're good, right? There's no ddx, so you're fine. This, you need to keep going, take a derivative, and then we'll put it together and be done. What is the derivative of 3x squared minus 1? What do we have there? 6x. Fantastic. So we're going to have 1 over 3x squared minus 1 times 6x. Where's the 1 go?
Turns to 0.
Yeah, sure. The derivative of any constant, always 0, so we're good on that. Put it together, make one fraction out of it. I pray that you get the right answer here. Can I simplify anything? Can I start crossing out 6s and 3s?
No.
It still happens sometimes. I swear I still catch people at this level. Yeah, don't do that. Please don't do that. Unless you can factor out and simplify, we're good. Do you all understand the first example?
Yep.
You okay with it? Not so bad, right? It's very much like chain rule, it's just you have a new function now. It's not even a hard function either. It's just you put 1 over the inside and you're basically done. Let's see how much we can step this up. Okay, that looks nasty enough. I think we'll start there. Give me some ideas on what you could do with this. True or false? Let me ask you actually. True or false? Can I move this cube root from the outside to the inside as a 1/3 power? Can I do that?
No.
No. If it was 1/3 ln x, absolutely. But remember I told you about not making up your own mathematics? Don't make stuff up. If it's not on one of those properties I gave you yesterday, you can't do it. So, no, I can't move it here. That's not what this is saying. What this is saying is that this is supposed to be the derivative of ln x all to the 1/3 power. Do you guys see the difference there? It's not here. We can't move it forward. It's not an exponent of the inside of our logarithm, of the argument of our logarithm. It's that whole log x, or ln x, raised to the 1/3 power. Okay, now you tell me what to do. What do you think?
Substitute.
Chain rule. I love the chain rule. Chain rule says to do, you guys over here, what? What would you do here?
Take the derivative
Sure.
on the outside.
Take derivative outside. Do you guys see the similarity between the problem I just gave you and this problem right here? Or no? I know there's an ln over here, but what we had here, we had something to some power. Check it out. If I cover this with my hand, do I have something to some power? Then do the same thing. What do you do with the 1/3?
Move it to the front.
Sure. I don't even care what's inside. I know for a fact whatever's here, if it's differentiable, this 1/3 goes forward and something goes right here. What goes right there?
Negative 2/3.
How do you get negative 2/3? What's the operation?
1/3 2.1.
Minus 1.
On the inside, what's going to go on the inside? Do we take the derivative of ln now,
No.
or do we take it later?
Later.
Okay, so this we leave alone. Just like we left this alone, we leave this alone. But we're not done. What's the next thing we're going to do? Perfect. So we're going to show that right now. ddx ln x. So we understand, well, a cube root, yeah, it's still a 1/3 power, but it's not a 1/3 power on the x. It's a 1/3 power of the entire function here. What that means is that we have a chain rule, we have a general power rule, we bring the 1/3 down, no problem, we're taking a derivative, we subtract 1 from it, but then we don't forget that this stays the same on the inside of our function, and we multiply by the derivative later of the inside of our function. Now, this should be an easy one. What's the derivative of ln x? Fantastic. So we got 1/3 ln x to the negative 2/3 times 1 over x. You know, we can clean this up just a little bit. Of course, this is a negative 2/3, which means that you can take this whole thing and put it where? Yeah, we can do that. We could change it to a cube root of this to the second power if you want. So this, you might be done with the calculus, but clean it up just a little bit. Don't leave it so nasty. We could have 3x, no problem. We can have a cube root of ln x to the second. That's how I'd like you guys to write it. Make it clean. Typically, sometimes I let you do it with negative exponents. Most of the time I don't want negative exponents. I want them nice and neat. The only time that it's not the case is if it's just a super huge derivative and it would just waste your time to do it. So that's an appropriate answer. Show of hands if you feel okay with that one. Fun, right? Right? Lie to me, right? Okay, good. All right, let's keep going. So we know how to take derivatives of ln x. We now know that the chain rule still applies to that. Let's keep on working with it. This is kind of good practice because it gets you back in the habit of doing derivatives and you're learning something new. What do you think we're going to do first? What do you think? Is this like a general power rule like we had last time? Is it a chain rule still? Anytime you got a function instead of a function, it's a chain rule. Pretty much anytime you do a derivative, it's a chain rule. Sometimes it's easy because you just have x, but it's always some sort of a chain rule. So we have ln of some function. Tell me, people in the middle, what's the first thing that I should write here?
Break up the LN.
Okay, let's talk about it. Can we break up the ln? Can we break up that natural log?
Oh, no.
Remember that we can break up multiplication, division, and powers of the entire function inside the ln. Can we break this one up? Can you break up addition? Then we can't touch this. Dun, 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 dun. Can't touch this. Anyway, we can't break this up because of that nasty plus there. Ln of something plus something does not equal ln of something plus ln of something. It doesn't work. If that had been multiplication, of course we could, but we can't do it here. Do you see why? Okay, so now we got to do the derivative like it is right now. What would I do first?
1 over the inside.
Yeah, that's fantastic. This is a chain rule, right? The derivative of ln says you put 1 over whatever this is. I don't care what it is. That's how the chain rule works for ln. So the first thing, absolutely, is 1 over just that nasty stuff. Do you guys understand that that is the derivative of ln? That's what that says. ln just says 1 over the inside. That's all it means, okay? Now, to deal with the inside of it, you use the chain rule. So what are we going to do next?
Multiply by the derivative of the inside.
Perfect. I'm going to change that right now so I don't have to do it again. Instead of the square root, let's just make that the 1/2 power right now. Can you guys do that for me? Why don't y'all do that? Take care of that derivative. I'll write it on the board. I want you guys to try it on your own. I want to see if you got it. Did you get it? Did you guys notice that there's a double chain rule in here? It's awkward, right? But that happens a lot in calculus. We deal with one chain rule, boom, we got another one in there. Derivative of 2x is, of course, 2. We bring down the 1/2 power, leave the inside alone, subtract 1 from our power, and then multiply by the derivative of the inside. This sort of thing you can do without showing me the extra step. I want to see I want to see this stuff for ln because that's what we're learning. But those the ones that you should know already, feel free to just do them quickly, okay? I don't expect that we have any issues with this, I hope. Do we? Well, I hope not. Do you? Do you? Okay. If you do, you let me know. I can cover this a little more thoroughly. Do you guys see what I'm talking about, though? The chain rule at work? We have bring down, leave it inside, subtract 1, and multiply by the derivative inside. After this, it's kind of your job to clean this up. I'm not going to do any more work on this particular problem. What I would suggest, this gets really messy really fast when you have multiple chain rules, especially these negative exponents. This right here, of course, you can move this to the denominator. I'll show you one more step. But the rest of it, honestly, is just some algebra. You could do 3x squared over 2 square root of x cubed minus 1. Do you see how that works?
Yeah.
We can bring this down. That's a negative power. That's a square root, x cubed minus 1. This 2 is on the denominator. 3x squared goes in the numerator. Of course, you have to show me the parentheses there. That's important. But in order to make this one fraction, you'd have some work to do. You'd have to get common denominator here, and then put those two things together. That's kind of up to you. I would say that this would be fine for one of my answers in class. In the back of the book, like when you're checking your work or whatever, it might not look like this. Most of the time, they do the extra work. They make the common denominator, they distribute, they combine like terms, they make one fraction out of it. So if you want to get yourself really good at algebra, try doing stuff like that. You guys okay with this one so far? So calculus is done. The only thing you'd have to do now, just a little bit of algebra. Y'all have any questions, or can I move on?
Move on.
We good?
Yeah.
Am I going too fast for you? You're okay. All right. Tell you what, we'll do about 3 more of these, just to get your heads wrapped around some of these other concepts I want you to know. We'll talk about a new technique that you probably haven't ever seen before. We'll talk about implicit differentiation, and then we'll do logarithms. Oops. Oh dear, here we go. First things first here, let's look at our problem. When you're doing derivatives or integrals, it's really good to spend some time and diagnose what's going on. Sometimes these are going to be pretty easy, but you still want to think about them. What's the big idea on this derivative? Does ln contain everything in this problem?
No.
Then it's not a good idea to start with ln first. It's a first good idea to start with, say it again?
Product.
Yeah, a product contains all of this. You guys see it? We have x cubed. Anytime you have something in front of ln, works just like something in front of parentheses is being multiplied. So there's a product right there. Do you remember? Remember the product rule?
Yeah.
Show me the product rule here. Go for it. Write it out. Product has a P in it, plus has a P in it, so product plus. So product rule, you're going to have to add something together. So I'm going to show my work that way you see where everything's coming from. Product rule works like this. You do the derivative of the first times the second plus the first times the derivative of the second. Some people do it backwards. Some people do the first times derivative of the second plus the second times derivative of the first or whatever. I prefer it this way. Just that's the way I grew up learning it. Derivative of the first times the second plus the first times the derivative of the second. Did you remember it?
You know,
If you didn't, that's okay. We're just starting here, but relearn it right now because you're going to use it a lot. All right.
say it again.
Say what now?
Say that again. The derivative of the first times the second
Derivative of the first times the second.
plus the derivative of the second plus times the first.
Sure. Yeah.
Or something like that.
Something like that. It's one of those things. Derivative of the first times the second plus the first times the derivative of the second. Derivative of the first one times the second one plus the first one, leave it alone, times the derivative of the second one. So you take a derivative of one of them, you leave one alone, add, take a derivative of the other one, leave the other one alone.
Oh, the quotient is the.
Quotient first happens when you have a quotient.
Right.
Low D high minus high D low, square the bottom, away, we're done.
Wait, that's quotient rule.
That's the
Yeah.
quotient rule.
I remember that.
It works for quotients. Product rule for products. But product rule, your derivative of the first times the second plus the first times the derivative of the second, add them together. That's the idea. I don't really care the order in which you go. Make sure you're taking the derivative of one of these factors, multiplied by the other one, add, take a derivative of the other factor, multiplied by the first one. That's the idea. Now, the derivatives themselves should be pretty straightforward. You let me know. X cubed, what's the derivative of x cubed?
3x squared.
Sure. So 3x squared, you'll notice we leave ln 5x alone. We don't do anything with that. Then we have this add. We have x cubed times, how about the derivative of ln 5x? What do we have to use there? It is the chain rule. So chain rule here says, what? Perfect. Times, sure, I'm going to show it right now just so we get used to doing that. Times the derivative of 5x. Some people forget to do this. If you forget to do this, you can change your problem a lot. You have a 1 over 5 instead of 1 over x. Okay, you have something different here. So 3x squared ln 5x, no problem. Plus, how much is that?
5.
What happens to our 5s? That's what I mean about you have a 1/5 when you're not supposed to. How about our x's?
Oh, 1. That's about 1.
Simplify the things that you can. So if we have x to the third here and we have an x down here, we can simplify that. Sorry, I know I did a whole lot of simplification all at once, but if you need this one more time. The derivative of 5x is 5. Simplify the 5's. We still have an x, we have x to the third, that makes x to the second. Show of hands if you're okay with that one. What's one more thing you could do if you felt like doing some extra math here? What could you do?
Take out the x squared.
Good, you could factor it, that's right. You could factor this out and get 3 ln 5x plus 1 x squared on the outside. Do I care? Not really. If you get a different answer in the back of the book, maybe that's what they do, so just be aware of that. Can we move on? Do you guys have any questions at all? Are you getting your brains a little bit uncobwebbed with some of this stuff? It's going to take some time, it is, but don't worry about it right now. You'll get there, okay? Derivative ln absolute value cosine x. One thing I want you to notice is that sometimes we have absolute value around our function, sometimes we don't. Really, when it comes down to it, don't worry about it, because when I gave you the definition the very first time, you don't need to write this, you already have it in your notes. When I gave you the definition the first time, I really gave you the definition of ln absolute value of x is 1 over x. So we don't really need to worry all that much about those absolute values. It's just there to make sure that it's telling you, hey, don't worry, you don't have any negatives inside of your natural log function because we can't have those. Of course, cosine has positive and negative, correct? So when they give this to you, they're saying, we're just focusing on positive cosine. That's what we're talking about, all right? So don't worry too much about that. Let's worry more about doing this derivative. First thing, ln is the overarching function. It contains everything here. So let's take the derivative of the ln. Y'all should be pretty good at this by now. We've done a few examples. What's the first thing I'm going to write? 1 over cosine x is absolutely true. Yeah, for sure. 1 over cosine x. You'll notice there's no more absolute value. The derivative of absolute value x is 1 over x. So that goes away. Don't need to worry about that one. Are we done? No, this is what again? Sure, so we're going to do the derivative. Oh, we should be pros at this. Derivative of cosine x. Come on. Come on. Oh, I heard some people say the nasty one and some people say the right one. I know it's sign somehow, right? Is it positive or negative? Negative. Very good. So this is going to be 1 over, oops, that's not right. 1 over cosine x times negative sine x. Let's put that together. We got negative sine x over cosine x. Say it again.
Negative tangent of x.
Perfect. That's tangent. This is tangent, so this is negative tan x. Cool, that was interesting, wasn't it? So sometimes these logarithm functions of sine functions gives us other, logarithm functions of trigonometric functions gives us other trig functions. It's kind of weird, but a lot of those relationships show up with ln's, and it's really interesting. Can we do one more? Okay. Is this good practice for you? Are you getting something out of it, I hope? All right, good. I don't want to waste your time or my time. Should I stop there?
No.
No. Don't worry, I haven't gone crazy. I know, right? It's crazy. Now, I think you'll agree, that looks pretty bad to start with, right? It does to me, at least. You go, my goodness gracious, that's not fun. Well, I want you to think about what we can do and why we did the whole yesterday's lesson on learning how to expand and combine logarithms. In every other example that we had before, we can't expand it. We could have, but it really wouldn't have done anything here because that's pretty easy. We couldn't really expand it for anything reasonable. Definitely can't expand that. Can we expand this one? Yes. The more that you do, the easier that your derivative becomes. So expand these as much as you can. Then do derivative of each little piece. Man, these become way easier. I'm going to kind of cheat here. I'm going to do the whole expansion in my head right now. Hopefully you can follow me along. We're going to talk about it though, so stick with me. Notice the ln's over the entire thing. You need that. What do you do with this division? How do you separate that? So we're going to subtract off another ln of this piece. Are you with me?
Yeah.
Okay. What are we going to do about this product right here? So we're going to subtract, or we're going to add another ln on there. So we're going to have ln of this plus ln of this minus ln of this. Okie dokie. Maybe I'll do 2 steps for you. Notice one thing, when you're breaking up your ln's or your logarithms, you're not doing derivatives. You're not doing any calculus at all. So you still need that ddx. We're not doing anything right now except using the properties of logarithms. So please maintain this until you actually take the derivative. Once you take the derivative, of course, get rid of it. So we got ln of x squared, no problem, plus ln of 2x squared plus 1, all to the 3rd power, minus ln of 5 minus x squared under a square root. We'll make sure that's in the bracket because we want to take the derivative of the entire thing. Let's make sure I'm right. Am I right? Okay, let's plus this one because we had a product, minus this one because we had a quotient. Okay, should I stop here or should I keep going? Okay, keep going. The more you do, the easier this becomes. So let's keep on going. What should I do?
Move the
Power.
square root up.
Square. Fantastic. What else?
Move the square root up.
Square root. Okay, so that's a 1/2 power. I'm going to move that to the front. Cube to the front. Let's do this. So every one of these arguments has an exponent. Let's move to the front. let's look and see what we did. You should know that when you take derivatives, you can take derivative of each individual piece as you go. Is this derivative easy or hard?
Easy.
That's a piece of cake. This one?
Easy.
Pretty easy, involves a little chain rule, but not a big deal. This one?
Easy.
Also easy. We just made something that looks really nasty into 3 really easy pieces. Really easy pieces. That's nice. Try that when you get to those heavy-duty ones in the homework. You go, oh my gosh, what in the world? See if you can split them up. Now, don't split up things that you're not supposed to. For instance, can I split this up? No, it's got a plus. This one? No, it's got a minus. I can't touch those, but we definitely want to be putting our exponents forward. Definitely want to be separating products and quotients. Still okay so far? Okay, question?
Do you notice I added 1/2?
I don't think so.
When you bring down that 1/2, you subtract 1.
Okay, remember that right now we still have this ddx out front. It's telling us we're not doing derivatives yet. We're not touching calculus. All this was logarithm properties. So all this was, hey, remember how we brought the 3 down? We're not subtracting it because that's where exponents go. Remember how that's a 1/2 power? We're bringing down the 1/2 power. We're not subtracting because we're not doing a derivative right now. Now is the time where we take a derivative. Question?
I think what you said is because you used subtraction for the rule to expand it, and it was originally a negative exponent, so would it be an addition? Like, because it was at the bottom, the square root of 5?
No, it doesn't matter. Let's split, like when we did something like this, ln of x over y, we do ln of x minus ln y. This takes care of the negative exponent for us. Do you see why? You could actually write this ln x times y to the negative 1, correct? You can separate this by ln x plus ln y to the negative 1. That's an exponent. That goes down in front. ln x minus ln y. That's why that works, okay? That's actually a little proof for you. Didn't want to have to show that, but there you go. Does that make sense?
Yeah.
Okay. Now we get to do derivatives. What I want you to do is practice this. Do the derivative of this piece, and this piece. It's nothing fancy, it's just little chain rules. So show that to me, and I'm going to do it over here for you, okay? Did y'all get it already? Oh, good, all right. You know, I got space over here. Oh, let me think. So derivative means that because I can split up derivatives by addition, I can do that for derivatives. I get to do derivative of this, and then this, and then that. So I know I've got 2 times the derivative. Remember with constants, you don't need a product rule. If you did, the derivative of 2 would be 0, so that would kind of eliminate half of your product rule anyway. You don't need it for constants, only functions of x times functions of x. So no product rules here on any of this. 2 times 1 over x, no problem. 3 times, again, that's a constant. We have 1 over 2x squared plus 1. 1 over the inside times the derivative of the inside. 3 stays there. Derivative of ln of this nasty junk, we put 1 over the inside times derivative of the inside. Minus, again we leave the 1/2 there. Derivative of ln of 5 minus x squared. Well, we do 1 over the inside times derivative of the inside. Let's see what we got. I know I can put that together, that's 2 over x. I know that this, what's the derivative of that one? 4x. So I got 4x times 3, that's going to give me 12x over this stuff. None of it simplifies, so that's going to be part of my answer. You guys 2 for 2? Did you get both of them? Damn. How much is this derivative? What's that give you?
Negative 2x.
So this is, let's write that. This would be 4x. That's how we got the 12x. This, you said this is what?
Negative 2x.
Okay, so if we put this together, hopefully I'm not going too fast for you. Negative 2, positive 2, minus. What's the sign going to be for this fraction?
Positive.
Yeah, sure. Minus and negative gives us a plus. 2 over 2, those simplify out. So we're not going to have a 2 in here. We're going to have 1 over this. That's it.
X over.
Say what now? Oh yeah, x. X's aren't really that important, are they? I mean, yeah, okay, you're right, I forgot. So x over 5 minus x squared. Did I miss anything else? Let's double check. 4x times 3, that gives us our 12x. This stuff doesn't change. 2's are gone, minus with a negative gives us a plus. X over 5 minus x squared, we got that. That's as good as I want. How many people got that one? That's good. If you did that, you know what you're doing, okay? If you didn't, if you struggled a little bit, this is one of those times when before you start your homework, you should go back through your notes, do the problems that we've done in class. Like, don't just follow them, actually do them. Like, different sheet of paper, put your notes aside, see if you can do them. Do them until you can get it right, and then start your homework. I promise it'll be a whole lot easier if you can do that, okay? If you jump right into your homework, you go, I'm a little overwhelmed, because you never really learned the material. You need to learn the stuff before you try the homework, okay? You with me? The homework's there to kind of beat it into your head so you get the repetitive nature of this. Okay, are you ready for something a little bit new? This is cool. I promise you're gonna like this. This is nice. You really will. I do, at least. I think you're gonna like it. What this is called, this next little piece that we're gonna talk about, is called logarithmic differentiation. So when they ask you for that and you go, what in the world is logarithmic differentiation? That sounds horrible. It's really not horrible, it's actually kind of fun. This is what they're talking about. And it stems from this idea. Let's suppose that we have some sort of a function like this one. Question?
Is this still 6.1?
Sure is. I'll let you know when we change. We got a function like this one that, well, we could probably take the derivative of that, couldn't we? Just like it is? I think I could. You guys had it earlier, what you could do. What could you do here? Quotient rule would have to be done. Then you'd have a chain rule and you'd have a chain rule, but you can do it. It's not going to look very pretty, but you could definitely do it. But there's another option. If you have some of these derivatives, you go, man, it's kind of nasty, and they get way. This is kind of an easier example to do this with, but they get really nasty, okay? Especially if I had like another function of x up here, you'd have a quotient rule, then a product rule inside the quotient rule, then some chain rules. It'd get nasty really, really fast. Sometimes we can get around that, and here's how you do it. The way that you do is called logarithm differentiation. What you need to know is that you can do anything you want as long as you do it to both sides of an equation, practically anything you want. Well, one of those things that we could do, looks a little weird, but one of those things we can do, we can actually take an ln of both sides of our equation. Can someone out there explain to me why this would actually help us here? Aha! If I take an ln on both sides, this doesn't help us very much, but this does, because I can separate it. I can expand it all out. Are you with me?
Yeah.
Okay, so what we're going to do, before you start showing me derivative, before you start showing ddx or doing anything like that, you're going to expand this thing. So no ddx's right now, we expand it first. So what that means is ln y equals, well, let's see what we can do. We got a quotient here. What's a quotient change into, everybody, real quick? Subtraction, very good. Do we have any products here? No, but we have some exponents. We have a 4, and we have a...
1/3.
Cool, so I'm going to do all that right now. So we got ln 4 times ln of x minus 1 minus 1/3 ln 2x minus 1. Can you guys double check me, make sure I did that right? Okay, cool. Is that as expanded as we can get? Can we break this up? Please goodness sake, say no.
No.
Can we break that up? How about this one? No, we can't. We can't separate subtraction. So this, 4 came forward, no problem. This, we have subtraction, 1/3 came forward, no problem. Now we're ready to take a derivative. Do you remember doing implicit differentiation? Yeah, we're gonna have y primes everywhere you touch a function of y. You get that y prime. I like the dy dx because that's how I grew up with the Leibniz notation. But here's the idea. Check this out with me. We're gonna do a derivative of both sides. So here and here. You'll notice that our derivative is with respect to x, which means that we treat y as a function of x. What that means is that we do our derivative just like normal. So the derivative of ln y, what would the derivative of ln y be?
1 over y.
Very good, but check this out. Because this is a function of x, we have to show the chain rule. It is a chain rule here. So what this looks like is 1 over y for sure, but check this out, why you get the y prime. Why, and I don't really like the y prime because notation-wise it kind of fails you here. But notice, you would do a derivative of the inside. Does that make sense? You'd have, hey, 1 over y. This is the derivative of ln times the derivative of y. Look at this. This is dy dx. That's what that is. That gives you your derivative. So I'm going to go down here and give you dy dx. That's this side. That's all you got to do. So we have, how do you take a derivative of ln y? No big deal. It's 1 over y, just like always. But then you do a chain rule. Derivative of y over x. Hey, that's it. That's your derivative. This is what we're going to solve for in just a second. Now let's do the derivative of this side. This should be pretty easy. I want you guys to do it. Go for it. We'll do one more and we'll call it good for today's lesson. Oh goodness. Were you able to do this derivative?
Yeah.
Should get 4 over x minus 1. Did y'all get 4 over x minus 1?
Yes.
We do the chain rule, but the derivative of x minus 1 is simply 1. So this is 4 over x minus 1 minus, well, we got a 1/3 here. We've got a 1 over 2x minus 1 because we're taking a derivative of ln. But now we do have a chain rule. Don't forget about the chain rule. My goodness. Derivative of the inside gives you what? How many people made it that far? That's cool. That's great. It's fantastic. Let's clean this up a little bit. A couple things need to happen. Firstly, we have a 4 over x minus 1. We've got a 2 over 3. Don't forget parentheses here. We get a 2x minus 1.
Can you distribute that? Just can
You can distribute it. Generally, people don't typically distribute denominators because if you have to create a common denominator, it's easier to do it when it's factored. Okay, because here you distribute, but then to find a common denominator, you'd have to refactor it. So typically, people don't do that. It's not a big deal if you do or not. Okay. Now, the last thing. If you'll notice this, we haven't solved for our derivative yet. We have 1 over y times dy dx. What you need to do when you're doing this process, solve it for dy dx. This stands for your derivative. So if you get this by itself, you're done. Tell me, how can I get this piece by itself? Fantastic. So if I multiply by y, and I multiply this whole thing by y, well, these are gone. That's cool. We get dy dx equals, I'm going to leave all this stuff the same. 4 over x minus 1. 2 over 3, 2x minus 1. Times y. Okay, I want to show of hands real quick if you're okay with what we've done so far on the problem. Good, that's fantastic. Now, question for you. is it appropriate, if I can change the y, should I leave the y the way it is? Or would you rather see function of x? Right now this is implicit. If I can solve for an explicit derivative, that's a little bit better. Look back at our problem. Do you know how much y is equal to?
Yes.
Do you?
Yeah, x
You should. How much is y?
Minus 1 over square root of that.
That bunch of crap. Hey, look at that, we got it. So all you gotta do, I know it's fun. I told you it was a fun day. Sure, we took ln both sides. That's so that we can split all this junk up, okay? We split all the junk up. We took a derivative after that. Notice here's our ddx. This is where you do calculus. Calculus, this side is implicit. Calculus, this side is pretty easy. Put it together as much as you can. Solve for your derivative, whatever that is. If you used y prime, no problem. Solve for y prime. Solve for dy dx here by multiplying y on both sides. Now, just make a substitution. This should be explicitly defined somewhere. In fact, it's right here. So this piece goes here. If we do that, then we're done. I really don't care how nice you make this. You're going to find out that your derivatives can look quite different from the back of the book. Right now, I'm not trying to get you to be super excellent at algebra. I'm putting this stuff together. You really should know that. So you should know how to find common denominator and put that together, okay? I'm trying to get you to be good at the calculus part of it. And that's really our goal here. So I'm going to leave it with these two fractions. You need to know that you can manipulate it a little bit. So we'd have 4 over x minus 1 minus 2 over 3, 2x minus 1, big old bracket, and then we multiply by however much the y is equal to. Since the y is this stuff, that's what we put on the back end.
For like test reasons, will you mark us down for not doing the y what it equals to, or like we put a y prime
Yeah,
instead of
absolutely.
dy dx?
I do want, the y prime is perfectly fine,
Alright.
but I do need you to notice that this is a function of x. This should be substituted back for. I don't want you to leave it y. I want you to, because this is what logarithmic differentiation is. It's kind of going around the derivative, but still getting a proper derivative in terms of x. Okie dokie. Are you guys okay with this idea? Question?
So if we leave it like that and don't do the algebra, we're fine?
This is fine for me. I need to tell you that in the back of the book, typically what they'll do is they will find a common denominator. They'll put this together. It's going to look a little bit different because they want one fraction if possible. Do you see what I'm talking about? If they get one common denominator and put this together, then you could make one fraction out of it. Now, I'm not going to spend the time to do that because we could spend all day doing things like that. Show of hands, feel okay with it? Okay. Now, the last thing we're going to talk about, we've got about 2 minutes here. I want to show you something like this. I don't know how much we're going to get through. I'll probably just go pretty quick at it, but I want you to think through this. Firstly, can you think about this as an implicit problem? Do you guys see that we have x's and y's all tied together and we can't really get them separated? Okay. There is one thing that we can do to make a problem easier. What is it? You have it. It's in your head. I can see it.
The ln separate?
Yeah, the ln, absolutely. Let's separate that thing. That makes our problem easier. Do you guys see it? So we would do ln 2x minus ln y minus sine y plus x squared equals 0. That's as easy as we can get it, okay? We can't do anything really substantial to make this problem any easier. We could separate these, but it wouldn't make a difference because that's a constant. Who cares? Derivative, that thing's going to be pretty piece of cake. So we would take a derivative of both sides.
Now, would it be easier to separate the x's and y's on their respective sides?
You can. It doesn't really matter. You're going to do it at one point or another, okay? So here, I'm going to be kind of quick about this. I really don't want to keep you over. So derivative of ln 2x, can you tell me what that is?
2 over 2x.
Sure, it's 2 over 2x. It's 1 over 2x times 2 because we have the chain rule. Here we have minus 1 over y times y prime. If you like the prime notation, that's y prime. Minus, derivative of the sine, everybody, derivative of sine real quick. So we would have cosine y, but check this out please. Because you took a derivative of y, you're going to have a y prime, plus this one, derivative of x squared is?
2x.
Perfect. Derivative of 0?
0.
Cool. 2x, cosine y prime, 1 over y prime, 2's are gone, we get 1 over x. All you have to do now, get all your x's on one side, factor your y prime just like implicit differentiation does, and you're done. So, let's see. If we do that, we're going to have a 1 over y times y prime, cosine y times y prime. On the right-hand side, we have a negative 2x minus 1 over x.
How'd you get,
You see negative
What?
y.
What'd I do?
you put 1 over x plus?
What are you talking about? Just checking. As soon as you have your y prime terms on one side and everything else on the other side, this is when you want to factor out your y prime. And then just divide. So I guess the long story short, break down the ln's as much as you can. Break them down. Then start taking derivatives. Whether you need logarithmic differentiation, okay. Whether you need implicit differentiation, okay. If it's implicit, you're not going to get many of these, but if it's implicit, make sure you take and do a y prime or dy dx everywhere you take a derivative of y. Get all those terms to one side, everything else to the other side, factor out your y prime, divide typically, and you're done. This answer, by the way, it can look different. You need to know something about this. You can multiply and get a common denominator. You multiply, get a common denominator, do a complex fraction on that, and it's going to look a little different. What I want to know is everyone okay getting down to at least this far? So hands if you are.
Yes.
Is it making sense to you?
Yes.
Okay.
And so we don't need to put y.
All right, so now it's time to keep going with our natural logarithms. We've learned all about the derivatives. We did a lot of examples from that. Now we're going to start talking about integrals. So if you remember, the first thing I actually proved, other than just the properties of logarithms, was the integral and derivative of that. So what we should have down, I think you guys already have this, but we'll talk a lot about it today. Our goal was to find out what in the world happened when I take an integral of something like 1 over u. We tried that, right? We did it at first and went, man, this didn't work like the normal way we were to do this. We can't make this u to the negative 1 and then add 1 to it because we get u to the 0, we get 1 over 0. That's a big problem. So we said, well, how are we going to do that? So we did the whole ln thing. We said, well, this really is ln of the absolute value of u plus c. Do you remember the absolute value that we had? Okay, so that's the integral that we're talking about. The integral of 1 over u gives you ln absolute value of u plus c. That's what we're working with today. What I want to do is just practice a few very basic examples with a little bit of substitution for right now, and we'll gradually work our way up to some trig functions and see how that works for us. You guys ready?
Yeah.
So, first thing. Let's consider integral of 1 over 5x minus 2 dx. Now, if you remember back to your integrals, your idea was, and we haven't really learned any integration techniques yet, you're still in the same boat. The boat being, you either have to have something that's directly on your table. Remember the integration table that you guys have? I know some of you had the little sheet out right now. You either have to have something directly on your table, like x to the third, or just secant squared, or something like that. Or you have to substitute to make it fit your table. Well, here's one more thing that we have added to our table. So if we can make it look like this, then we can do the integral. Does this look exactly like this? No, it doesn't. So if it doesn't look like that, we've got to make it look like that. What's a good way to make it look like that? A substitution is fantastic. Remember how substitutions work. Substitutions work when you look at a part that you don't like in your problem, like this. I don't like that part. and the derivative of this part has to be somewhere in your function, disregarding the constants. So what's the derivative of this?
5.
But there's no x's, right? So that's cool. We can pull 5's out in front. That's the idea. We're going to make a substitution to make this guy look like this guy. So our substitution here has to be u equals 5x minus 2. Let's see what, oh, you know what? I want you to practice that too. What do we do when we do a substitution? What's the next step?
And du dx.
Yeah, okay, because we have to not only substitute for this, but we've got to change this as well. This has to match up with whatever variable you are substituting for. So yeah, we need a du equals 5 dx. I learned it this way. You guys can do your substitution however you want. I learned to solve for dx, so you'll always see me doing du over 5 equals dx. Some people have done it another way. It's fine. I don't care what way you do it, okay? So we'll do a substitution. We still have a 1. What does the 5x minus 2 become?
U.
Good. And instead of dx, I put
du over 5.
perfect. What do you typically do with that 5?
Move it out to the front.
Yeah, that way it doesn't affect any of your, or make it more difficult or anything. Makes it a little easier. So 1/5 integral of 1 over u du. We want to make sure this matches this. Your variables have to match. Did we make it look good? Now does it fit part of our table?
Yep.
That's fantastic. That's the whole idea here. So don't trick yourself into thinking these things are ridiculously hard. Right now, pretty much all you know is it either fits your table or you substitute to make it fit your table. That's about it. So we did a little substitution. I know the 1/5 stays there. That doesn't affect anything. Everybody, integral of 1 over u du is?
ln. Put
ln.
absolute value u.
Good. Absolute value is important. Plus c, sure, you can put that now or you can put it at the very end. It really doesn't matter. There is one thing that is important though. What variable did we start with?
An x.
What variable do we have now?
Take u.
That's a problem. So what are you going to do?
Put x back in.
Yeah, so if we have this substitution, u equals 5x minus 2, that u becomes 5x minus 2. So our integral is 1/5 ln 5x minus 2 in absolute value plus c. Okay, that's our first example. It's a really simple one, but I want to make sure that you guys are okay with it. Show of hands if you are. You feel okay with that one. Perfect. Fantastic. Let's step it up just a little bit. I want you to know that we're not always substituting just to make an ln. Sometimes we're going to have, 1 over u to get an integral that equals ln. Sometimes we'll have ln in our integral, so let's practice one of those too. All right, looks a little scary, but let's look at it. The first thing you should do whenever you do an integral is see if it fits your table. Is this anywhere in an integration table that you know of? No, it looks pretty nasty actually. There's a square root, there's an ln x, it's got a fraction. That's like all the bad stuff at once, right? That's no good. But then we think if it doesn't fit the integration table, we should look to make
Substitution.
That's right, let's make a substitution here. The appropriate substitution is one that's typically inside another function. It's usually like a denominator, or it's inside parentheses, or it's inside a root. It's usually inside something, and the derivative has to be there disregarding constants. So let's look at the appropriate substitution. Is the appropriate substitution 3x?
No.
No, the derivative of that is 3. That's not going to help us with our ln. Is the appropriate substitution the square root of ln x?
Yeah.
With the square root?
Yeah.
No.
It's typically not the whole function, guys. It's typically the inside of a function. You take the ugly part out. Here's what I mean by that. Look. If you had a u in here, could you take the integral of u to the 1/2 power? Yeah, so don't worry about that square root. Also, the derivative of ln x, I'll think back to yesterday, the derivative of ln x is?
1 over x.
Here's a 1, do you see it? Here's a 1 over x. That's something that we're looking at. So you want the derivative to be in there, and typically they use the inside of some other function. So let's try it. U equals ln x, and you already told me that when we take our derivative, we're going to get du equals 1 over x dx. Again, I always solve for dx. You don't have to, but you can. If I multiply both sides by x, I get x du equals dx. Do you guys see what I'm talking about? About your derivative has to be there? Because right now when we substitute this in for dx, our x's are going to go bye-bye. And what you have to have is all one type of variable, and that's got to match up your du or dx or whatever you have. You guys ready to do the rest? So let's see. You tell me what I'm going to have. Do I still have a square root?
Yes.
Square root of u.
Inside that square root is?
U.
Mhm. Denominator, I got a 3x still. I haven't changed that yet, but I have an x du. Yeah, that's right, the x's do. So x's are gone, that's fantastic. We had to have that happen. If that doesn't happen, you've made the wrong substitution. Okay, you have to get rid of all the other variable or be able to substitute for it in a different way. You have to have these things match up and have no other extraneous variables going on. Tell me one other thing, two other things that we're gonna do on this problem. 1/3 goes out, what else?
Change the square root to the 1/2.
Perfect, square root to a 1/2. So 1/3, no problem. We've already got rid of our x's, that was a big deal. We've got u to the 1/2 power du. Be careful when you're doing your integrals, remember that we're always adding one, we're not subtracting, that's a derivative. So when we do our integral here, we got 1/3, no problem. We've got u to the...
3/2 times 2/3.
2/3.
Good, times 2/3. Where we're getting the 2/3 from, I'm going to show it here. This would be over 3/2. But then what you know is you got a complex fraction. The 2 just moves to the numerator. So really we've got 1/3 times 2/3 u to the 3/2. Nothing simplifies here. We've got, hopefully I did it right, 2/9 u to the 3/2 plus c. And we're done, right?
You gotta put the,
Oh.
where u is.
We're not done. We're close to done. We're almost done. The last thing we got to do is make sure that if we've done a substitution, you got to substitute back for it. So since we did all the way back over up here, we're going to put this back for this. Then we'll be done. By the way, is my math all right?
Yes.
Okay, good. So we've got 2/9. Yeah, ln x. We'll just move that 3/2 up like that around the whole thing. One quick question. Can I move this 3/2 to the front? Yes or no?
I'm gonna say
Yes or no? What do you think?
No.
Yeah, you can, it's not
Oh,
in that
let's see, yeah.
thing.
3/2 from the bottom.
You can't.
Okay, so question. Is this the same as this?
No.
No.
Okay, this one you can, this one you can't.
Okay.
This is the whole function raised to the power. Does that make sense to you?
Yeah.
Okay. So be careful on that. Again, don't invent your own mathematics, please. Plus C, that's done. Show of hands, feel okay with that one? Boom, fantastic. That's really, I'm only going to give you two of these ones. They're pretty basic. You're typically going to use a substitution. You're either going to have something like 1/u to substitute, I'm sorry, after a substitution, or you can substitute ln x. See if you can work around with that. Of course, I can't give you every type of example you're going to have, but these two cover a lot of bases here. So look for substitutions. Try to make it fit something that's in your integration table. Now the next one. Now it gets fun. This is the good stuff. I know you've been waiting for it. I know you've been waiting for the trigonometry, right? Right? Am I right?
Yes.
I know. Well, so far, here's a couple of them that you know. We know this one, and this one, and this one. And we know, I'll just do a few, just these ones for right now. We know this one. Let's practice, see what you guys know. Let's start with this one. What's that?
Sine.
How about that one?
Negative cosine.
Good. Oh, you guys are good at this. Some of you in the math lab took my advice and actually learned these when I told you to. That's fantastic. How about...
Tangent of x plus a.
Good.
Secant of x plus a.
Okay. Thanks, one of us. There's a couple other ones. What's another, give me another one.
I think you got cosecant, cotangent,
Yeah, that's the one.
and then cosecant squared.
What's this one?
Negative cosecant.
That's right, negative cosecant. And then the last one should be cosecant squared, right?
Yeah.
Let's see. If secant squared equals tan x, cosecant squared should equal co something.
Cotangent.
Cotangent.
Negative cotangent.
Negative, and it's negative, that's right. That right now is your integration table for trigonometric functions. I believe that's about all that's on there, right? We're going to create some more right now. So this is what you're kind of expected to know coming into this class. Everyone from your verbal responses knew these ones, yay! But these ones are a little bit harder to memorize because we don't use them as often. We're going to use these, okay? We're going to use them, so get used to them. Write this down, have that in your memory banks. You okay? Okay. Now, what we don't see up here is stuff like this one. We don't see the integral of tan x. If you've wondered, why in the world don't we ever see the integral of tan x? Why couldn't we deal with that? Well, we're going to find out right now why you couldn't deal with that in Calculus 1. So, give me some ideas on how we might go about, now that we know some of the stuff that we do know, how we might go about solving this particular integral. What would you want to do first?
Break it up into sine, cosine.
Good, we'll use an identity. You'll find out that with trig, you use a lot of identities. I wasn't lying to some of you who came to me earlier and said, what do I need to know? Learn your identities. Learn your identities because we're going to use a lot of them. So yeah, let's break it up. Tangent is sine x over cosine x. Go through the steps I'm talking about here. Now we're going to look at this. Does this fit over here exactly? Does it fit over here exactly? No, it doesn't look exactly the same. If it doesn't look exactly the same, then you're going to use...
Substitution.
Yeah, you're going to make a substitution and make it look the same. Okay. Well, let's do a substitution here. Now, it's true that the derivative of sine is here, but if I solve for it, it wouldn't cross it. It wouldn't simplify that out of the problem. So, u being sine's probably not a good choice. We want to pick the worst part of this and call it u. In our case right here, we're going to pick u equals to cosine. Cosine x. Do you guys see what I'm talking about the worst part of this? Being cosine is on the denominator. Also, it's a great part for us because if I do the derivative of cosine is, and besides the negative, the sine part's right there. That's something we're going to be able to simplify out. So that's a good choice. So du equals negative sine x dx. You know me, I do du over negative sine x equals dx. Let's see what this does. Do we still have a sine? Well, it depends on how you do the integral. For me, yeah, I still do because I like to do this. Do we still have a cosine?
No, wait, no.
What's our
U.
cosine? Do we still have a dx? No, du for me, or sorry, dx for me is du over negative sine x. Our sines are gone. Tell me a couple things that we're going to do.
Move that negative out to the front.
So this is negative integral 1 over u. Man, that made it a lot nicer. Can we do the integral?
Now you can.
We can now because we learned about what? We learned about that thing. What's that thing? We learned about lns. That's right. We learned about natural log. So, notice we do have the negative ln of... You're forgetting something.
Absolute value is
Absolute value is absolutely important. Okay, that's cool. We're almost done. Let's go one more step. I think someone else said that already. You can't just leave it in terms of u. What are we going to put in place of our u?
Cosine.
So this equals, I'm going to go right over here so it looks better. This equals negative ln absolute value cosine x plus c. Show of hands if you feel okay with that one. Isn't that interesting? I think I told you, I think I prefaced this last time and said, it's really weird, but a lot of trig functions get related to ln somehow. Don't you? It's interesting, isn't it? That when you take the integral of tangent, you somehow get ln of absolute value, negative ln absolute value of cosine. You guys okay with that one? It's pretty straightforward, right? Now, there's one more thing that we're going to do here. What does this count as? What does that mean? That is an exponent. So if this is a -1, then really what we can do, we can move that as an exponent. So this is ln absolute value cosine x to the -1. Tell me something.
Move that into
How much is that equal to? You should know it.
1 over
1 over cosine. Very good. This is 1 over cosine. 1 over cosine is also known as
Secant.
secant.
That's right.
So, we get another identity for us. What we know now is that the integral of tan x dx is equal to ln absolute value secant x. Let's see. Some people out there might be wondering, wait a second, isn't this a problem because if I plug in pi over 2, that's 0. Are you with me? You should know your trig, right? If I plug in pi over 2, you get 0. So wouldn't this be 1 over 0? Isn't that undefined? And the answer is, yeah, it would be, until you consider where this is coming from. Tangent is not even defined at pi over 2. It's continuous, and it's defined between, not including, negative pi over 2 and pi over 2. Remember those S-curves that you get? So we don't really have to worry about the pi over 2 because you wouldn't even be able to integrate it anyway. Does that make sense to you? Okay. You might not have thought of that, but there it is. So we got another one. So we got these ones. Now we got integral of tangent equals ln secant, absolute value secant x plus c. Here's the deal in this class. Once you prove something, you don't have to keep redoing it. So next time you see the integral of tangent, or you see something that has a tangent in there, don't reinvent the wheel. You don't have to break it up into sine over cosine. We just did it. Anything that we prove in class, like this one, you can use. So now use that. Keep that in mind next time you do your homework. You go, oh, okay, how about the, we're not going to do this one, but how about the integral of x tan x squared dx? Well, you're thinking substitution for the x. Now that's in your table. You're good to go. Does that make sense? Makes it a whole lot easier than having to go through this all the way over again and again. You guys want to see one more? Did you like that one? It's kind of interesting, right? It's kind of fun. Tell you what, we'll do, run out of room here. I think we can do this. This one's tricky. It's really tricky. It's tricky because we use a trick here that I wouldn't expect you to know. I didn't know it until I saw it. So if you're like, wow, where's that coming from? So was I the first time, okay? What we're going to do here is we're going to multiply by 1 in a really, really unique way. We're going to change the look of this thing. And we're going to change the look so that we can use a substitution that actually makes sense. Because right now, doing the 1 over cosine thing, we're just going to get stuck in a rut. Because if you do 1 over cosine, are you familiar with the 1 over cosine here that I'm talking about? Yeah. If you do 1 over cosine, you do a substitution for cosine to get the 1 over u. The sign doesn't eliminate. So you'd be stuck in a rut, back and forth and back and forth. It's like a catch-22, okay? So we're going to do a nice little trick here. Instead of just having secant x, what I'm going to do is I'm going to keep the secant x, and I'm going to multiply by secant x plus tangent x on both the numerator and denominator. If you're like, Leonard, what in the world are you doing? It's a trick that we're going to use to create a substitution. All right, I know it looks weird. It's like, how would you even come up with that? I didn't come up with it myself, honestly. I read it out of the book. I'm like, oh man, these tricky guys, you son of a gun. You did it. Well, here's the deal. And you're going to see it right away as soon as we distribute this numerator. Notice numerator gets distributed, denominator does not. So we have here secant squared x plus secant tangent, secant x tangent x. You guys okay with the distribution? Yes, no? Yeah. Secant squared, secant tangent. Here's why we did that. I want you to look at what's the worst part of this. What's making this harder than it needs to be? The denominator is. The denominator is the bad part here. If we do a substitution for this, what's the derivative of secant?
Secant squared.
Oh yeah. What's the derivative of tangent?
Secant.
Oh, sorry, I had these backwards,
That
but
whole thing.
what's the derivative of secant?
Secant x times
That one. What's the derivative of tangent? So if we do it together, we're going to get that whole piece out of it. Does that make sense? We're inventing a substitution here. It's a little awkward because, yeah, it's hard to see it. It's, wow, how in the world? But someone figured it out and we're just going to use it. So if we do u equals the denominator, secant x plus tangent x, and we do a derivative, again, let's try this. Derivative of secant x, everybody, what is that?
Secant x
secant
tangent
x
x.
times y.
Very good. Plus, so we did this is that part. Plus, that's right, secant squared. I'm going to do the substitution a different way. Some of you are familiar with this. You look here, you go, okay, dx, I try to look for this stuff too. Do you guys see that this is this whole part right here?
Yeah.
That's our substitution. That's awesome. I love this game. So we do a substitution. We have, tell me what the integral is now. What's on the numerator?
1.
Yeah, 1. One's, or du, sure. Over, what did we call this?
U.
And then this whole thing became that du. So you either have du over u or you have 1 over u du. Either way is fine. Can we do the integral now?
Yeah, you can.
Now it's a piece of cake. ln absolute value of u plus c, no problem. The only thing that we're going to do is what?
Put the u back in.
Yeah, put it right back in there. So what we know now is that the integral of secant x dx, got it from there, is ln absolute value. Remember, this was our u, secant x plus tangent x. Plus c. That's the reason why you didn't get a whole bunch of these things in your Calculus 1 class, is because you can't do them. You can't do them until you learn about what the integral of 1 over u is. Once you do that, the whole world opens up for you as far as trigonometric integrals. Did I explain this well enough for you? Show of hands if I did. You're okay with that one? What I'm going to do now, I'm not going to prove all of them. I'm just going to complete this list for you. That way you have the entire thing, okay? So we just did tangent. We just did secant. There's a couple others I want to give you. So add on to whatever list you have the following things. First one we already did. We know that the integral of tangent u du is ln absolute value secant u plus c.
That's not the same thing as saying x.
You know, it is the same. The reason why they have it as u is to let you know that you can make a substitution and change it into that. So you can put an x or a u. Actually, all of these should probably be u's. I think it's that way in the integration table in your book or whatever you're using. My bad, I just did them on top of my head, so I used x because I'm used to it. Use x or u interchangeably. The reason, again, why they're using u here is to let you know that a substitution is possible in them, so don't forget about that. In other words. One we didn't do cotangent u, but I hope that you understand it would be really, really similar to tangent. All you'd have is cosine over sine, you do practically the same thing, and you're going to get this. This one we did do. This one we did do. Did right over there. So this would be ln absolute value secant u plus tangent u plus c. And last one, again, you see what I'm talking about the cotangent would look really, the proof would look really, really similar to this one. Well, the cosecant proof would look really, really similar to this one. It's similar to that one. So we have ln absolute value cosecant u minus cotangent u. And there's some similarities here. Instead of secant, we get cosecant. Instead of tangent, we get cotangent, and the plus we get minus. It's kind of like the reverse of all of my suppose if you wanted to call it that. Show of hands feel okay with these ones. I'm not going to prove them. The proofs are really similar, so you can either do them on your own, look them up. I think some of them are exercises for you. What I do want to do is 2 examples that illustrate how you would go about doing these. Would you like to see some?
Yes.
Okay, so you guys like tattoos, right? Just get an arm tattoo. It'd be the coolest thing like ever. No? You would be able to. Can you rip your arm off? Then yes. Do it. I won't give you extra credit, but you'll be awesome. Just tell them it's some sort of like, I don't know, Japanese writing. Most people wouldn't know the difference. Just tell them it says honor and strength. I did have a student once who came to school. I gotta tell the story. Came to school, like, he wore the same shirt, like, I think 3 times in the class, and it was Japanese writing. He was not Japanese. He said, hey, what's your shirt mean? He goes, oh, I really don't know. And so I had 2 Japanese students. I'm like, do you know what that shirt? He left class to use the restroom or something. I said, do you know what that shirt means? He's like, yeah. I said, what's it mean? I don't want to tell you. I'm like, no, come on, tell me. It means I want a girlfriend. So funny. He had no idea. Classic. That was a funny day. I never told him what it meant. Anyway, I don't want to make fun of him. That would be mean.
It's not making fun of him.
Okay, so let's start with our problem. Does it look exactly like something in our integration table?
Yeah.
No, it's got x's. It's got an x squared there. It doesn't look like that. So if it doesn't look exactly the same, you're going to do what?
Substitution.
Let's do substitution. What's the appropriate thing to substitute for here? Good, yeah, it's usually the inside of something. The derivative is always in the integral. You don't want to pick the whole thing because then you're going to get a trig function that's not in there again. So that would be a problem. So typically try the small stuff first, like x squared in this case. So if we substitute for x squared, of course, du equals 2x dx, du over 2x equals dx, well, then we have an x still here, depending on how you substitute, secant u du over 2x. Is it going to work out for us? Yeah, the x's are gone. It's fantastic. Tell me what else we do.
1/2 in front.
Yeah, 1/2 secant u du. Look what our substitution did. What it did was it matched this up with something that we just learned how to do. You don't have to reinvent the wheel all the time. That'd be ridiculous. So as soon as you do your substitution, now you start looking at your table of integration. You go, oh, well, how much is that? Do you know how much that is? Do you know what the integral of that is? I think I'm covering it up. It's right here. Sure. So we still have the 1/2. We've got an ln. We've got absolute value, sure. Secant u plus tangent u plus c. The reason why they use the u's here is because you are probably going to use the u's here. That's a lot of u's. Do yous understand me? Joking. Anyway, the last thing that you want to do though, please don't forget to substitute back in. A lot of people when they're doing this, they either do u's and they go, I'm done, that was so hard, oh, I'm finally done. Or they just put x's right off the bat. You don't want to do that either. Okay, so what goes here and here?
X
X
squared.
squared.
Yeah, so our answer is going to be 1/2 ln absolute value secant x squared plus tangent x squared plus c. You guys all right with that one?
Can you put that 1/2 as an exponent as well?
You can, not such a big deal, I don't really care about that. It is an exponent. It would be the square root over all this stuff, all right? Not super necessary for you to do that. Good question though. Any other questions before we go on? You ready for one more? Does anybody else need this? Okay, cool. Okay, this one's going to bend your brain a little bit. You have to think about this one.
That's another identity.
And you go, wait a minute.
This is
Crap.
gonna be minus.
Well, that definitely doesn't look anything like anything in our integration table right away, right? So we're going to have to do a substitution. Let's check out the appropriate substitution. Should it be 2x? No. Because if I do that, it's not going to get rid of any of this stuff. Should it be the numerator at all? No, because if I do this, it's not going to touch this down here. So probably it's going to be something down here. Now, let's talk about the denominator. If I pick the entire denominator, let's try the derivative of that. What's the derivative of 1? Well, that's fantastic. So when we have that, get rid of that 1 for sure. Can you do the derivative of sine squared? Oh, come on. What rule is that?
Chain rule.
It's a chain rule, that's right. Do you remember that sine squared x means sine x, all of it squared? We'll bring down the 2. We'll leave the inside alone. We'll multiply by the derivative of the inside. Are you with me?
Yeah.
We'll bring down the 2. We'll leave the inside alone. We'll subtract 1 from it, and we'll multiply by the derivative of the inside. I want to know if you're okay with 2 sine x cosine x. Do you, not so much? Derivative of sine x squared. That's what this means. You have to know that part, okay? If we do the derivative of this, this is 2 sine x to the first power times the derivative of sine x. What's the derivative of sine x? 2. This is meaningless. Cosine x. That's our appropriate derivative. Yes, no? I know I went fast on that, but that's old stuff. Are we okay with it?
Yeah.
Okay. Now wait a second. Does that even help us?
No.
Explain why.
Well, because sine of 2x, the trig identity for that is 2 sine of x cosine.
Woo! I love those identities. Don't you love those identities? This identity right here, this is 2 sine x cosine x. That's the identity. It's double angle. You got to know those identities. If not, you got to refresh your memory like now. Okay, go home and start. You guys like tattoos, right? Just joking. You have a lot of tattoos. Let's see what happens here. Okay, I forgot the dx. Sorry. Let's see what happens. Let's do the easy part. What's this become? Mm-hmm. If this is, you know what, I'm going to do this in 2 steps. I'm sorry. I'll do it in 2 steps. The first step that I've done here, it's just the identity. I've just changed this into this. If you don't know that identity by heart, you can look it up later. It is a true identity, okay? So this is true. At this point, I would do my substitution. Now check out what happens. I have a 2 sine x cosine x dx. That's exactly this piece. So this is going to change into my du. So I get du over u.
So
1 over u du, or du over u, it's the same thing. Okay, I don't want to go too fast on that one. I didn't make sure that you guys are with me. Are you comfortable with this identity now that I've told you that it's true? Are you okay with picking this as your u? If you are, then the derivative is 2 sin x cosine x. That's literally exactly what we have here. So this piece becomes du, this piece becomes u, and that's a really, really easy integral. How much is that integral?
ln of the absolute value.
Yep. We got one more thing to do. We're going to,
Put the u back.
so final answer, ln absolute value 1 plus sine squared x plus c. It's actually technically not the final answer. We're going to do one more thing with this. One more thing. I want to make sure you're okay with this so far though. Are you? The last thing we're going to do is we're going to drop the absolute value. Do you know why?
Because it can never be negative.
That's right. It can't ever be negative. This is always positive. If you add 1 to something that's always positive, it's always positive. So the absolute values are kind of redundant. You can do that if you know your argument's always positive. So we could write this instead as just ln this stuff plus c. And that's probably how you'll see it. We good? That's it. That's 6.1. We're done. So we just started off our ln. We know how to take derivatives and integrals. Do I have any questions whatsoever? How many people feel okay with the idea? Do you guys have questions?
No, you're true.
So now you know how to do derivatives with ln, yes?
Yeah.
Just do 1 over inside times derivative inside. Integrals a little bit more labor intensive. You have to do some substitutions, especially with trig stuff. You're going to get a lot of trig stuff in this class. Get used to it. Learn those identities and learn how to use them, okay? So right now, what we're going to start section 6.2.